Hello and welcome. Today, we are tackling one of the biggest, most fascinating challenges in all of AI. How do we actually understand the decisions these incredibly complex systems are making? We're going to peek inside the mind of an AI and uncover a really powerful tool that makes its reasoning surprisingly, and I mean surprisingly clear.
So, our story here kicks off with what looks like a simple little puzzle, but you'll see it quickly reveals a massive problem, right at the heart of modern AI. Okay, so take a look at this. We've got an AI reading movie reviews. It correctly figures out that this movie is not bad is a positive review. Makes sense. And it also correctly identifies this movie is not very good as a negative one. But the question is, how did it figure that out? I mean, the sentences are practically identical.
And that, right there, brings us to the core issue. We can see the final answer, right? The output. But the internal logic, the why behind the decision, is completely hidden from us. This is famously known as AI's black box problem.
Now, you can bet researchers have been trying to crack this black box open. But the first attempts, well, they were a bit like a detective finding clues that just don't add up. They only made the mystery deeper.
So, one of the more popular methods for getting these clues is a tool called LIME. Now, what's really interesting and kind of weird about this is that when LIME analyzes our first sentence, "This movie is not bad," it actually tells us the word "not" is contributing to the positive rating. That feels odd, doesn't it?
Which of course leads to the critical question, when does that rule even apply? When is the word "not" a positive thing? The clue isn't just unclear, it's kind of confusing.
And this is where it all just gets messy. We ask LIME to explain the second sentence, "This movie is not very good," and now it says, "not" is the single biggest reason for a negative review. So, which is it? The clue completely contradicts itself. It's confusing, it's unreliable, it's not helping. But then, a breakthrough. A new, much clearer way to understand the AI's logic. It was time to drop an anchor. So, what is an anchor? Think of it like a super simple, high-precision if-then rule. Its job is to find the absolute smallest group of words that are enough to lock in the AI's prediction. Once those words are in place, the rest of the sentence almost doesn't even matter.
Okay, let's go back to our movie reviews and see how this just solves the mystery instantly. For the first sentence, the anchor rule is if the words "not" and "bad" are present, the prediction is positive. For the second one, if "not" and "good" are present, it's negative. It's simple, it's logical, and best of all, there's zero contradiction.
And this just brilliantly illustrates the difference. A LIME explanation is like a fuzzy circle. You're not really sure where its influence begins or ends. But an anchor creates a clearly defined box. You know exactly when the rule applies and when it doesn't. The coverage is perfectly clear.
So, we've seen how anchors totally nailed our movie review puzzle. But how does this powerful tool work when we throw completely different types of problems at it? Let's take a look.
Check this out. Here, anchors show us that an AI has actually learned some basic English grammar. For the word play, the anchor is just the word that comes before it. So, if the previous word is a determiner like the AI knows play as a noun. If it's a pronoun like I, it knows play is a verb. Pretty neat, right? This gets even more interesting with data you might find in a spreadsheet. For a model predicting recidivism, an anchor reveals the exact rule it's following. If an individual is male, black, with 1 to 5 priors, and not married, the model predicts they're likely to be rearrested. This gives us a crystal clear and maybe even troubling window into the model's logic. In a lending model, an anchor can show a more nuanced rule. A FICO score in this specific range combined with a loan amount in that specific range leads to a good loan prediction.
Now let's see how this works in the visual world. An AI looks at this photo and correctly says, yep, that's a beagle. But what parts of the image, what pixels, made it so sure?
And the anchor reveals the exact pixels that locked in that prediction. And would you look at that, it's not the whole dog, not even close. It's just these specific disconnected patches on its head, its body, and its paw. As far as the AI is concerned, these pieces alone are enough to scream beagle.
So here's where things get really crucial and a little bizarre. What happens if we take only those anchor pixels and change everything else? Well, if we drop them underwater, the AI is still over 90% sure it's looking at a beagle.
Or even if those same pixels are superimposed on a person lifting weights, it doesn't matter one bit. As long as that anchor, that sufficient set of pixels, is present, the AI confidently predicts beagle. It really shows you how literally these models apply their rules, completely blind to the context around them.
Now, these examples are fascinating, for sure. But why does any of this really matter? Well, it all comes down to a single critical concept: trust.
And we actually have the data to back this up. In a user study, people were asked to predict what an AI would do. When they were given anchor explanations, their accuracy shot up to nearly 100%. But with those older Lime explanations, their precision was way lower, down around 68%. That's a huge difference.
And not only were they more accurate, they were way more efficient about it.
It took them less than half the time to make a prediction using anchors compared to Lime.
I mean, that makes sense, right? A simple if-then rule is just so much faster for our brains to process. And the final verdict from the users themselves? Well, when they were polled, an overwhelming 21 out of 26 said they preferred using anchors. The evidence is pretty clear.
Which leaves us with this final thought. As AI becomes more and more involved in everything, from medical diagnoses to loan applications to who gets a job, we have to ask ourselves, if we can't clearly understand the why behind its decisions, how can we ever truly trust it with the things that matter most?
All right, welcome back. So in our last explainer, we got the hang of what anchors are, right? These simple if-then rules that tell us why an AI made a certain call. Well, today we're diving into the really cool part. How does a machine actually find these rules all on its own? So here's the plan. We're going to start with the main problem, then figure out what makes a perfect rule. After that, we'll walk through the search step by step, see how to make it even smarter, and wrap up with some really wild examples from the real world. Okay, let's jump right in. The first big hurdle is, well, it's basically like finding a needle in a haystack. See, for any single AI prediction, you could dream up a nearly infinite number of if-then rules to explain it. The real trick, the whole game, is finding the one that's simple but also really powerful. So, let's look at this sentence. This movie is not bad. An AI model looks at this and, yep, it correctly figures out the sentiment is positive. But the real question is why? What was the clue? What part of this sentence was the actual key? And this is where it gets tricky. I mean, just from that one sentence, you could come up with all sorts of rules. Is the magic word not? Or is it bad? Or is it the combo of not bad together? Trying to check every single possibility would take forever. It's just wildly inefficient. There has to be a smarter way to do this. So before we can even start looking for the best rule, we have to agree on what best even means, right? We need to set some clear goalposts for our algorithm. And it really boils down to two key things. First up, precision. It has to be super high. Basically, when our rule fires, it needs to be right pretty much every single time. We're talking a target of over 95% accuracy. If the rule says the sentiment is positive, the model's prediction better be positive, no exceptions. And second, we need good coverage. Think about it. A rule that only works for this movie is not bad is, well, it's pretty useless, isn't it? A great rule is one that you can apply to lots of different situations as long as those key ingredients are there. And this is the whole goal boiled down into math. Now, I know the formula looks a little intense, but the idea behind it is actually pretty simple. We want to find a rule, let's call it A, that has the biggest possible coverage. But, and this is the crucial part, we have to be super sure that its precision stays above our target, say 95%. It's this constant balancing act. Go as broad as you can, but never, ever let the accuracy slip. Okay, so we have our goal. Now, let's get into the really clever part, the step-by-step process the algorithm uses to actually build one of these anchors, literally from scratch. And the process is, surprisingly straightforward. It starts with an empty slate, then it creates a bunch of candidate rules by just adding one word at a time. It tests all of them to see which one has the highest precision, adds that best word to the rule, and then just repeats. It keeps adding the next best word piece by piece until the rule is strong enough to meet our goal. So, step one, we start with literally nothing, an empty rule. Now, this rule technically applies to everything, so its coverage is 100%. But its precision, yeah, it's probably not very good. Then, for step two, the system looks at our sentence and generates all the possible one-word rules it can. So you get a rule for this, one for movie, one for is, and so on. Each of these is now a candidate, and they all have to be tested to see how well they predict that positive outcome by themselves. Okay, step three. After testing all those single-word candidates, let's say the algorithm finds a winner, the word not. That means out of all the individual words, not is the single best predictor, the one that most reliably points towards the model's positive prediction. But a rule with just the word not probably isn't going to hit our 95% precision target. So the process repeats. Now, starting with not as the base, it creates new two-word candidates, like not movie or not bad. It tests these new combos and discovers that adding the word bad gives it the biggest jump in precision. And boom, the new rule. If you see not and bad, finally gets us over that 95% line. The search is over. Now, this step-by-step approach is pretty good. It's a great start, but it has a weakness. It could take a wrong turn early on and get stuck. So to make the search even smarter and more reliable, the final algorithm has a couple more tricks up its sleeve. This part is actually really fascinating. The way it tests all those candidates, it uses something called a multi-armed bandit strategy. The analogy here is perfect. Imagine you're in a casino, and each possible rule is a different slot machine. Your job is to find the one that pays out the most, the one with the highest precision. But you want to do it by pulling the levers as few times as you can. It's all about being strategic. And to make sure it doesn't get stuck on a bad early choice, the algorithm uses another technique called a beam search. So instead of just picking the single best option at each step, which is kind of risky, it keeps, say, the top 5 or 10 best candidates in play. It explores all of those paths at the same time. This makes it way more likely to find the anchor with the absolute best coverage, not just the first decent one it stumbles upon. All right, so now that we know how it works, let's see what this thing can actually do. Because the results you get in the wild on everything from text to images are seriously powerful and sometimes pretty surprising. Check this out. Here, anchors are explaining a model that figures out parts of speech. And look at the rules it discovered for the word play. It found that if the word right before it is something like a, then play is a noun. But if the word before it is I, then play is a verb. I mean, the model basically taught itself grammar, and the anchors lay that logic out for us, crystal clear. It gets even more interesting with data and tables, like for loan applications. Anchors can show you exactly how the model is thinking. Like here, it's clear. A FICO score below a certain number is enough for the model to predict a bad loan. But what's really powerful, and frankly really important, is that this can also uncover some uncomfortable truths. This method can expose when a model is relying on sensitive features like race or gender to make a prediction, giving us this crucial and sometimes alarming window into a model's biases. Okay, this is just brilliant. This really shows you how it all works for images. On the left, you've got the original picture of the dog, but look at the image on the right. That's the anchor. That's it. The algorithm figured out that all the model needed were those specific pixels, basically just a bit of the face and the collar, to be 95% sure it was looking at a beagle. To the AI, apparently, everything else in that photo is just background noise. And here's where it gets really wild. What's fascinating is what the model doesn't seem to care about. They took those essential beagle pixels and slapped them on a completely different background, a coral reef, and the model is still more than 90% sure it's a beagle. It really shows you that things we humans think are essential, like having legs or not being underwater, just aren't as important to how this AI sees the world. Which brings us to a final, really important question to think about. If an anchor reveals that a model is biased or just plain weird, does that mean the model is broken? Or does it mean the explanation is working perfectly? I'd argue it's the latter. When these tools show us the flaws, they're doing their job, giving us exactly the transparency we need to debug these systems and hopefully build AI we can actually trust.